I'm going to talk about some work I did for the Australia-Indonesia Centre in relation to rural electrification, which had a focus on Indonesia. In Indonesia, there's about 40 million people not connected to the grid, and there was about 3 or 4 million people who have no electricity of any kind. And so the government has been working with PLN, the electric utility, to try and expand the grid into the remote areas, try and build electricity infrastructure in eastern Indonesia, which has even lower levels relatively of supply. And of course, as you know, batteries and solar panels have been falling in cost over the last decades and are expected to continue to become less expensive. So the question is, should the government start in the villages and put in solar battery systems with maybe some diesel support, or should they focus their efforts on extending the grid? And the process of sorting all that is still very difficult because it's political, it's economic, and the objectives within the country are not always aligned between the central government and the regions. So what I thought, I was given a free hand for 12 months. So some of my colleagues were looking at the grid extension side of it, including the socio-political issues. And I thought, well, what does this remote system look like if you just got solar panels and batteries? So I thought I'd have a go at building some models. So I thought the questions I was thinking about looking at were, what's the optimum deployment of batteries and solar panels, and can you build some simple models that will solve that? And once you've got that sorted out, how do you work out what the efficient clusters are? You know, how close the buildings have to be before you'd say, well, let's build a DC link between them or an AC supply, and then distribute the batteries and the panels in the most efficient way. So my focus was to try and get some metrics around that to get some better understanding. And I had intended to use PLEXOS for this purpose. But what I found was that when I read the manual and applied what the manual said, it didn't work. And I remember the day when I set up my first single house PLEXOS model, and my boss Ariel was sort of, you know, panting, sort of waiting for the hot result, and I pressed the button and PLEXOS ran, and I got an array of zeros. So I thought, okay, that's not terribly informative. And fortunately, Glenn's been very supportive working with me over the last 12 months. It took him about 6 months to understand what I was even saying, which is probably my fault. But eventually I got the message through about what my vision was. And in respect to PLEXOS, we now have some sensible methods for formulating random variables that are suitable for this purpose. And most importantly, we can link random variables to conditions to other random variables in a chain, so we can build up a much more complex stochastic model of loads and solar operations, which I will attempt to explain. And I think probably this aspect of it will be of most interest to you. As it turned out, because I did not have the capability to get the PLEXOS working, I ended up building models in Excel, which in the academic community is a real downer. Apparently you say Excel and they immediately think your work is of lower standard. However, I'm stuck with Excel because I've been using it for 30 years or so, and so I'm pretty good at building models in Excel. So I'm pretty confident these results make sense. So let's move on. So let's look at the demand formulation. Well, in this case, I started with no metered information on demand, nothing. So what I did was I looked at some of the literature on how people have modelled electricity in residential buildings and commercial buildings in the developed countries, and I thought, how can I apply this in Indonesia? So I came up with the idea of starting with a household activity. You can actually get more complicated than that and have an individual activity for each person, but I had no insight at even about household activities in Indonesia, so I thought I'd start at that level. I could find information on appliance ownership in Indonesia at various levels of income, and there was also some surveys on amount of energy used for different household activities. Some of that was built around using kerosene, but obviously kerosene energy can be replaced by electrical energy with the right appliances. And I also had information on appliance characteristics. So what I did was linked the activities to the appliances. I had to do a bit of heuristics on how you allocate, say, activities for laundry and housework into the various equipment that you use for that. So that was a bit of guesswork, but obviously you would do that in a more informed way if you had the survey information. I then built a stochastic model for the load and the appliances, and I also applied the logic that if you wanted to use an appliance but there was no supply because the battery was flat and the sun wasn't shining, that if the sun shone, enabling the battery to be recharged in the next 8 hours, then you would defer that activity for up to 8 hours. So my model include deferment like that. I haven't quite figured out how to do that in PLEXOS in the optimal fashion, but that will be one of my future learnings, no doubt. And I applied, instead of applying an arbitrary level of reliability, I just costed the unserved energy at $5 a kilowatt hour, which was a bit of a sort of a guess number, and deferred energy by $2.50 a kilowatt hour. So if I used the energy later, there would be a cost on that dislocation of having to do it later. So on the supply side, I used 320 watt panels, which is probably too big at the lower levels of consumption, but I was trying to keep it simple. I talked to some folk in Indonesia about lithium ion versus lead carbon batteries, and they said they're deploying lead carbon batteries quite economically in some applications, so I set up the model with those at either 0.9624 or 4.8 kilowatt hour sizes. I put in a cost for the separate infrastructure for setting up the battery space and the electrical metering and so on, or switchboard and things like that. I didn't have really good information on that, so that aspect of the model could be improved. I analysed the solar model, with the standard equations for orientation and inclination, so I could work out what the clear day profile would be at any location anywhere in the world. Actually, my model does, but I focused obviously on Indonesia. And what I did was then simulated combinations of panels and batteries, not by any sophisticated optimisation, just enumeration in the space of potential feasibility. I then, having solved the optimum design for single houses, I then put those two models together with a zero cost link. I worked out the losses equivalent to about 100 metres as a bit of a guess about what the optimum or the maximum distance for connection might be. And then I resolved those two single house models to work out what the configuration would look like if you made a link between two houses. And I'll show you the results of that. So electricity consumption, I had information on how household consumption per month varied with average monthly income in Indonesia, and the data was sort of pretty straight through there, and just put a logarithmic function through that. And I also had some information on typical consumption levels in parts of Indonesia. In eastern Indonesia, the average consumption, and these are households connected to the grid, are about 125 kilowatt hours per month. And in Java, Bali, it ranges, expected to range up to about 170 kilowatt hours per month. And I also had some data at this sort of lower level down to about 10 kilowatt hours per month, which was about what you would expect with a single solar panel, and you use it to charge your mobile phone battery and you run some lights at night. You don't have a fridge or an air conditioner, you might have a little 50-watt fan or something. So I then put that together into a set of functions that this was the usage data for 4 levels of consumption that were available in a survey, and I kind of linearised and extrapolated that to give me a range from $10 to $200 kilowatt hours per month. And so, for example, air conditioning, which is the big green line, doesn't really start until about 60 or 70 kilowatt hours per month, and at a very low level. Things like fans, which is the red one, that's pretty important part of consumption across the range, but falls away as you move into air conditioning. And things like lighting is a fairly stable proportion relative to consumption levels. So that enabled me to build up over a wide range of 10 to 200, roughly what the profiles look like. The pure guesswork was, what does activity look like? I identified from the data I had 7 different activities: sleeping, cooking, eating, personal care, laundry, housework, entertainment, and absence. And I just invented these profiles. Have no idea whether they're right. I wasn't able to talk to anyone in Indonesia about this. So anyone here who's from Indonesia, let me know if you think that's really screwy. But generally people sleep at night, even in Indonesia. And I'm sure they eat during the day, and I'm sure they cook at various times. And they probably do more of their housework on the weekend than they do on the work day. I think everybody lives like that, don't they? So that's really kind of not difficult. So this model is purely probabilistic. And so this is when I tried to apply this in PLEXOS. I found that the previous method where you can set up a cumulative probability distribution and you sample a random number and you pick the nearest value, that didn't always work with this configuration. So I talked Glenn into changing it so the cumulative distribution is now less than or equal to. And now you can do any arbitrary distribution and sample it in PLEXOS. Win number one. So when I then modelled all the appliances, then that built up an average load profile on the work day and the non-work day. Interestingly, a bit flatter on the non-work day, and a maximum peak potential for the time of day. So as you know, with domestic load profiles, they're very volatile, and the peak load is up to 5 to 10 times higher than the average load typically at any time. Of course, when you put hundreds of thousands of domestic profiles together, it's all a lot more stable. But this represents the full stochastics, which is important if you're only trying to model one profile.
So, Ross, are you trying to displace a diesel generator that's already hooked up?
No, I'm starting from nothing, just putting in solar panels and batteries. I didn't model diesel, and then looking at the results for a small cluster of houses, it's actually cheaper than going for diesel anyway. But even in Indonesia, especially in Indonesia, it's very difficult to deliver diesel oil to remote locations anyway. There's a high transport cost, there are transport risks, and I'm sure there are areas where if people could afford it, this is what you would do. Actually, diesel power would be even more expensive than this. Solar energy model is pretty straightforward, based on latitude, longitude, orientation, rating of the panels. I put in a bit of allowance for shading. I wasn't really sure how to do that. The trouble with shading is it's very specific to the location. And so there was a bit of guesswork on that. And I allowed for the direct and diffuse insolation. I was able to find a site in Jakarta which had an 11 kilowatt system. And on pvoutput.org they publish the daily energy production. And I'll explain how I used that in a minute. The way I have modelled the solar energy, and PLEXOS is now set up to do this, is I have two random variables. One random variable to sample the daily energy, which is more dependent on the day-to-day weather profiles of is it sunny, when do the clouds move in. And you can get fairly consistent autocorrelation parameters for daily energy up to about 3 days. Although I found when I looked at the data, probably you only need one autoregressive parameter just from the previous day, but I've modelled 3 just to generalise it. So you sample the daily energy by an autoregressive method, which gives you a pattern of day-to-day energy which looks remarkably like the actual data. And then I use the sampled value of the daily energy to set the mean for the daily profile. So the daily profile is then sampled between the maximum and the minimum, which is about 5% of the maximum, with a high correlation of about 50% trading interval autocorrelation and a 30% standard deviation. And so that gives you the samples, sort of distributes the daily energy into the trading intervals. And that's a comparison of one example where the purple is, the red is the target daily energy and the purple is the sum of the trading intervals. And it's about right. It follows it about right. Probably not as exact as I'd like it, but it reflects the natural variation anyway. So you end up getting the right energy and you get a typical profile of the trading intervals. Batteries are pretty straightforward. I modelled 3 kinds of battery sizes. Typical cycle efficiency, which was split into the energy on losses on import and export, unit cost and infrastructure cost. So the unit cost of the battery is essentially the replacement cost of putting a new battery in once you've put in the infrastructure. I put in a technical life of 10 years and 3 1/3% annual energy capacity degradation. Now this slide is a bit busy, but the method of solving it's really trivial. If you think about it, if the sun's shining and I've got surplus power, what do I do with it? I charge the battery. If the sun's not shining and the battery's flat, what do? I shed load. If the battery's flat and I wanted to do something, I just track the next 8 hours, and as soon as there's enough charge in the battery to do what I wanted to do 3 hours ago, I do it starting with the largest load block. So I just work from the largest load block down to the smallest. So just take the solar power, the load, compare on the half-hourly basis. Am I in surplus or in deficit? If I'm surplus, I recover any deferred services I wanted to do. If there's any left over, I charge the batteries. And if there's too much, well, I record that as unused solar energy. If I've got a deficit, I shed load or defer load. I draw on the battery as much as I can. If I flatten the battery, then I've got unserved load. I then price that at the unserved energy cost. I mentioned $5 a US kilowatt hour. Add the infrastructure cost, gives me the total cost. And then I just put a little algorithm around that to look at all the combinations of batteries and solar panels in a feasible range to check what the lowest cost combination is. Now, the way I did that was I optimised the design for every one of 15 years, allowing for the degradation of the solar panels and the degradation of the batteries. And in year 11, I replaced the batteries with new batteries, the same as the start. So I did an optimal design. I chose an optimal design for every year of the 15 years. This is a bit like a scenario decomposition method. And then I looked at all those best year designs and chose one which had the lowest present value cost over the whole 15 years. So observations. Well, first of all, the problem is that the costs well exceed the income below 20 kilowatt hours a month. And the costs are about 63% of income at the average national consumption of 130 kilowatt hours a month. So clearly, if the government wants to roll out this technology, it's going to require huge subsidies, or alternatively, the electricity has got to dramatically increase the income of those people receiving this service. So there's major issues around the utility of doing this electrification. How is it going to be funded and what benefits does it bring? One thing I discovered was that some really logical things that you could kind of use to do a really quick design. From the solutions, I found that the battery power and the solar capacity are closely aligned. So if you put in a kilowatt of solar panels, you should put in a kilowatt of battery. The battery storage energy capacity is about 1 to 2 times the average daily demand. So that kind of makes sense. So the battery, when it's full, will get you through 2 days if the sun completely blocks out, but it never would be completely. The battery unit size increases with demand level over the range, as you'd expect. But interestingly, the log of the unserved energy had a very simple characteristic. And what I did was I found a regression equation for the log of the unserved energy, which closely modelled all of the solutions. And interestingly, it's almost linear versus 2 parameters, the battery storage capacity in kilowatt hours and the average solar energy per day. So and for the deferred energy, it also had a very almost linear characteristic. You can detect a slight amount of curvature in that function. So very, very useful, because what that means is that having done a set of simulations using all this random complexity, because the infrastructure cost is a linear function of how many batteries you put in and how many solar panels you put in, plus the infrastructure cost, you can then recover all of these designs and interpolate in between in about 1.5 minutes in a little Excel model. So very easy to then generalise it to other household sizes. And these are some of the characteristics that we got. So single house designs, the number of panels obviously starts from 1 at the low level. So here this is oversupply by a long shot. And then you've got medium-sized batteries in the middle, larger batteries there. The peak supply and demand shows the solar capacity and the battery capacity. The red and the blue lines are closely aligned, so that makes sense. The model peak demand is shown in black. So the solar battery capacity just sits under the peak demand here, and there's, they kind of add up together in this range here to meet the peak demand. This is the income equation. So that's the average cost of electricity from about $1.40 a kilowatt hour at the lowest level down to about 46 cents, 48 cents at this level. Grid electricity in Indonesia is about 11 US cents a kilowatt hour delivered, so it's about 4 times the subsidised cost of grid electricity in Indonesia. And the average cost per month in dollars and the income is shown here. So not till you get about here does the cost fall below the income. And interestingly, the battery capacity versus daily demand was almost a linear function over those solutions. So the two-house interconnected value, the way I worked that was take the single house models, look at the single house simulation, re-optimise the demand by taking away panels or batteries, then compare the costs between the two-house simulation optimum design and the single house design, and then calculate what the maximum distance is based on the cost of connecting the two houses. And this is a beautiful thing. This is a surface chart of the result of the maximum distance between houses. And this scale is small to high, small to high. So at the largest consumption levels, it's only worth connecting houses over that are 20 metres apart. So at that point, they're better off just having separate systems because at that level, you've got about 11 solar panels and about 2 batteries, so you can closely optimise the design. Incidentally, in these solutions, about 30 to 40% of the solar energy was unused, and only about 60 to 70% was actually used, which means that if these microgrids ever get built and connected to an external supply, they'll immediately be able to dump a whole lot of renewable energy into the main grid. I didn't include that in the valuation or the optimisation, but that's something you could consider. As a contour map, it sort of is understandable. So the real value is connecting small houses to large houses, and that's only because probably the small house designs could be improved by using smaller solar panels. And 2 small houses, which is the peak at the end there, that just meant you could do the 2 houses with one panel and 1 battery, and it was worth connecting them up to about 130 metres apart. So that gives you an idea of how quickly to identify a cluster. One of the more complicated cases was where I intentionally changed the orientation of the panels on one house to be well off the maximum energy production and well off the data I deduced from the Jakarta data. And in that case, where if you were going to put the panels on the roofs rather than on a pole at the optimum orientation, then there may be the maximum distance of connection could be up to about 190 metres, so that would represent the value of putting the panels on the most favourable roof. The contour map for that is almost impossible to read, but it's a bit like a river valley, isn't it? So, based on these results, it looked like the range for connection was in the range of about 120 to about 190 metres. The design optimisation is more complex if you've got alternative orientations for the solar panels. So let me talk about the PLEXOS implementation. I had started working on implementing this in PLEXOS. I haven't quite got there. I was hoping to have some comparative results by today, but I didn't make it. I mentioned that Glenn's upgraded the modelling of conditions and stochastic variables, so you can link random variables into other random variables, and you can now build quite complex load objects in the new version of PLEXOS. The battery model was found wanting in 7.5. The degradation didn't work, and there was a mismatch between what was load and what was generation, but we've got all that sorted out. I understand in the new version 8.0, the degradation is now based on battery cycles, not based on time. So I'll have to reorient my solution to work with that, but it's looking really good now conceptually. So the daily energy range concept which I developed was useful because, as you know, in most places there's quite a strong seasonality in the solar energy. So you don't want to model the solar energy as an absolute value. You want to have it as a relative value between the maximum potential and the minimum potential. So I think the daily energy range concept will work probably with the same parameters over the whole year, but that would probably needs a bit more testing. So I used the normal distribution to sample the daily energy range and then applied that to develop the trading intervals, and that can now be done in PLEXOS. One thing I thought could help with the data preparation for these sort of models was to be able to just put the solar profile in for 1 year and have it automatically run for all of the years. In the version that I had, I couldn't do that. I had to put it in multiple times in the CSV file, but I understand that's now been fixed up. So you can just put the year, you can skip the year column, just put in month and day, and that data will then automatically apply to all years in the simulation. Also, the model that I've set up will probably need a huge number of objects, one for each house modelled. And another thing that I'd probably like to see is that once you've set up a random load object which you want to replicate at different locations, it would be nice to only have to put that into the model once rather than one for every node. Right, so next steps are to hopefully get someone to do the surveys and information that would better inform this model, and then try and formulate a microgrid planning method that takes advantage of the stochastic simulation, helps you to value interconnectedness, and then helps you then build up the aggregate costs for rolling this out on a regional basis. So I hope you found that of interest, and happy to take questions.